We tend to think of planets as permanent things, round, stable, and complete. But nature does not always build them that way. Some worlds are caught between creation and destruction. Some carry evidence of forms they no longer possess. Others exist in arrangements that once seemed physically impossible. And a few are changing so quickly that what astronomers observe may already be an earlier version of what remains today. These objects are not merely distant curiosities. They expose the hidden forces that shape every planetary system. Gravity can move a world far from where it began. Radiation can remove what once surrounded it. Heat, collision, and time can transform something familiar into an object that no longer fits the old definition. The more astronomers discover, the harder one question becomes. What exactly makes something a planet? The answer is no longer as simple as it once appeared. Subscribe to The Last Signal on YouTube for more calm documentaries about the discoveries that continue to reshape our understanding of the universe. Some of the most precise signals in nature arrive from objects that no longer resemble ordinary stars. One source sends radio pulses toward Earth with such steady timing that a delay smaller than a heartbeat can expose something hidden. Astronomers were not originally searching for distant worlds around it. They were studying the rhythm itself. The source was a pulsar, a rapidly spinning neutron star formed when a massive star collapsed and exploded. As it rotated, narrow beams of energy swept through space and crossed Earth at regular intervals. Radio instruments could translate the signal into something resembling a perfectly repeating beat. Each pulse arrived so predictably that the pattern behaved like a natural clock. Then the clock began to slip. The changes were minute, but they returned in a way that random noise could not explain. Something was pulling the stellar remnant slightly from side to side, around a shared center of gravity. That motion changed the distance each pulse had to travel before reaching Earth. A signal arrived a little early, then a little late, and the sequence repeated with mathematical consistency. It was like noticing that a flawless metronome had lost only a fraction of a beat, then realizing the missing fraction returned on schedule. From those delays, researchers reconstructed the influence of unseen bodies. The system called PSRB 1257 plus 12 contains 3 confirmed planets. 2 have several times Earth's mass, while the innermost body is much smaller. None were first seen as disks, points of light, or shadows crossing a glowing surface. Their existence emerged from timing alone. These were the first confirmed exoplanets beyond the solar system, yet they did not circle a calm, sun-like star. They moved around the compressed remains of a stellar catastrophe. The modern search for distant worlds began beside an object created by destruction. Picture 3 dark bodies following stable paths through a region filled with intense particles and sweeping energy. No broad golden surface rises over their horizons. No gentle daylight spreads across clouds or oceans. Instead, a compact point turns with relentless precision while invisible beams cross the darkness. The arrangement is orderly, but the environment bears almost no resemblance to the skies that shaped life on Earth. A massive star usually ends its life in an explosion powerful enough to tear apart nearby material, alter orbits, and strip atmospheres away. It would be unsafe to claim that the present bodies simply survived that event unchanged. One leading possibility is that they formed afterward. Some material may have remained bound to the neutron star, or fallen back toward it after the explosion. Over time, the debris could have flattened into a disk and gathered into new objects. In that interpretation, these are second-generation worlds assembled from what the earlier system left behind. Another possibility is that parts of the original arrangement survived in heavily altered form. The evidence does not yet settle the question. Their precise origin remains unresolved. What is clear is that planetary systems do not require the kind of living star our own world follows. New bodies can form or remain in orbit after the central object has changed beyond recognition. Sometimes a system may be rebuilt from debris, with new paths emerging after the previous arrangement has been erased. The high-energy environment makes familiar surface life extremely unlikely. Yet the importance of these bodies does not depend on habitability. They showed that formation can occur under circumstances astronomers once had little reason to expect. They also proved that an invisible object could be detected through the movement it forces upon something else. Here, the evidence was not a picture, but a pattern, as though gravity had written the hidden orbits into distant radio light. More than 3 decades later, the stellar remnant continues to spin. The signals continue to cross the dark. And around that precise compressed object, 3 unseen worlds continue to keep time. In this system, there is no single star resting at the center of the sky. 2 suns move around one another, and a planet follows a much wider path around them both. The arrangement seems unstable at first, because each member of the pair constantly changes position and pulls from a different direction. For a long time, binary systems appeared to be poor places for planets to survive. Too close to the pair, changing gravity can stretch an orbit, twist it, or eventually throw a smaller body away. Kepler 16b revealed that disorder is not the only possible outcome. The 2 stars orbit their shared center of mass, while the distant giant remains far enough away to circle them as one gravitational system. That shared center is not a solid point or hidden object. It is the balance point created by the masses of both suns. Each one moves around it, with the lighter member tracing the larger path. Farther out, the circling body responds mainly to their combined pull, rather than every small change separately. The result is a circumbinary orbit, a path that surrounds both members of a binary star system. The structure resembles a wide dancer circling 2 partners who are already turning around each other. The motions are layered, yet they can remain regular, because every body occupies a region where gravity allows the pattern to repeat. Kepler 16. B stays beyond the most disruptive zone near the central pair. From that distance, the rapid movement of the stars is softened into a broader, stable influence. The giant completes 1 circuit in roughly 229 days. It carries about 1/3 of Jupiter's mass and is somewhat smaller than Jupiter in radius. Those measurements point toward a cold gas giant, rather than a rocky world with an open surface. Popular images often place solid ground beneath 2 dramatic suns, but the real object is probably wrapped in deep layers of gas. Any view from within its upper atmosphere would be shaped by movement. One sun could appear brighter, while the other shifted around it. Their separation would change, their apparent speeds would differ, and the balance of light would never match a day on Earth. At times, the pair might seem close together. At others, they would spread apart and cast light from clearly separated positions. Shadows in a cloud layer could overlap, pull away, and change direction as the inner orbit advanced. This would not be random chaos. It would be a repeating geometry governed by distance, mass, and timing. Astronomers discovered the system through changes in brightness. The stars regularly passed in front of one another, creating eclipses with recognizable depths and intervals. Additional dimming appeared when Kepler 16b crossed in front of the stellar pair. Because the central bodies were moving, those planetary transits did not follow the simple repetition expected around a lone star. Their timing and duration shifted according to the changing positions of all three objects. That complexity became evidence. By comparing several kinds of dimming, researchers separated the stellar eclipses from the planet's passage and reconstructed the larger orbital design. The observation did more than add an unusual gas giant to a catalog. It demonstrated that stable planets can exist around binary stars when they occupy the right region. The central pair still creates a dangerous inner boundary, but stability becomes possible beyond it. A planet does not need one fixed sun. It needs a gravitational arrangement that remains coherent over time. Above the deep atmosphere of Kepler 16b, the light would always carry the movement of two stars. No shadow would obey the simple pattern seen on Earth. The sky would change continuously, yet the distant giant would keep following the same broad path. Two moving suns, one cold world, and an orbit that turns apparent disorder into lasting structure. Far from its star, HD 80606b moves through the slowest and coldest part of its orbit. The star appears smaller there, and the giant receives only a fraction of the energy waiting closer in. For much of its 111-day circuit, the planet seems almost removed from the violence that defines it. Then gravity begins to pull it inward. Its path is not close to a circle. It is stretched into an extreme ellipse, so most of the distance is covered unevenly rather than at a constant pace. Near the outer part, the giant moves slowly. As it falls toward the star, it accelerates with startling speed. The change resembles a pendulum spending most of its motion near one side before raising through the lowest point. Only here, the swing involves a planet more than 4 times the mass of Jupiter. The star grows larger in the sky with each passing hour. Stellar light strengthens, the upper atmosphere absorbs more energy, and the interval between calm and crisis rapidly disappears. At closest approach, the giant passes only a few million miles from the stellar surface. That is close enough for the star to dominate almost everything happening in the atmosphere. Infrared observations revealed that temperatures rose by hundreds of degrees over only a few hours. The orbit itself created the weather. The incoming energy did not arrive gently or spread evenly. It struck one hemisphere first, heating gases faster than the atmosphere could carry that warmth around the planet. Layers at different heights reacted at different rates. Regions already facing the star changed before more distant areas could respond. The result was not a gradual season like those experienced on Earth. It was a sudden planetary heat pulse. Imagine an industrial furnace opening around an entire atmosphere. The star would swell across the sky while the surrounding gas brightened in infrared light. Cloud structures, chemical reactions, and broad circulation patterns would all be forced to adjust almost at once. No ocean or continent would absorb the energy slowly. The whole visible envelope would be thrown out of balance before it had time to settle. Researchers used infrared measurements to follow that temperature rise as the planet approached and passed its nearest point. Those observations showed the heating directly through changes in emitted radiation. What happened inside the moving atmosphere had to be reconstructed through models. Calculations indicate that powerful winds and large atmospheric waves should form as the hot region expands and pushes against cooler gas. Some models predict a broad disturbance moving around the planet as the heated hemisphere attempts to share its energy. These are not images taken by weather cameras. They are physical responses produced in simulations that must match the measured rise and fall of infrared light. The distinction matters because extreme planets often invite descriptions more certain than the evidence allows. The rapid heating is observed. The exact wind speeds, wave shapes, and circulation patterns remain model dependent. Earth's seasons are driven mainly by the tilt of its axis. They arrive gradually as each hemisphere receives changing sunlight over many months. On this distant giant, the dominant change comes from distance itself. The planet spends most of its time far away, then rushes through a narrow region where the amount of stellar energy increases with astonishing force. A season that would unfold slowly on Earth is compressed into hours. The atmosphere has barely begun to respond before the planet is already moving away again. After closest approach, the star starts to shrink. The incoming energy weakens, though the heated gases do not cool instantly. Winds continue carrying warmth across the giant, while radiation escapes into space. The planet leaves the furnace behind, but it carries the thermal disturbance with it. Farther out, the pace slows once more. The star becomes a smaller source of light, and the atmosphere begins a long recovery during the colder stretch of the orbit. Nothing about the cycle is random. Gravity repeats the same acceleration, the same close passage, and the same abrupt heating each time the giant returns. Yet the atmosphere may never respond in precisely the same way, because clouds, chemistry, and moving gas can preserve the effects of an earlier encounter. The orbit provides the repeated command. The weather is the atmosphere's delayed answer. Eventually, the giant recedes into darkness again, carrying heat away while the star rapidly contracts behind it. On WASP 76b, evening is not a brief transition between daylight and darkness. It is a permanent boundary wrapped around the planet. One hemisphere faces the star without relief, while the opposite side remains turned away. The world is tidally locked, meaning the same side receives the full force of stellar radiation through every orbit. That exposure drives the day side above roughly 2,400 degrees Celsius. Under such heat, materials that remain solid deep inside Earth can enter the atmosphere as vapor. One of them is a familiar metal. Near the bright hemisphere, atoms of the metal can move through the upper air as part of a gas. As winds carry that material toward the evening boundary, the temperature begins to fall. What stays vapor in daylight may no longer remain suspended in the same form after crossing into darkness. Researchers did not watch iron droplets falling through clouds. They reached the interpretation by examining how starlight passed through different edges of the atmosphere. Spectroscopy separates light into its wavelengths and reveals where particular colors have been absorbed. Each element leaves a distinct pattern, much like missing notes revealing which instrument has joined a larger chord. When WASP 76b crossed in front of its star, part of the light filtered through the thin outer layers surrounding the planet. A high-resolution spectrograph measured the chemical fingerprints carried in that light. Neutral atoms of that metal appeared strongly near the evening boundary. The same signature was not found in the expected way near the morning boundary, where gas returns from the night side into daylight. That difference became the key. If the metallic vapor moves from the heated hemisphere, Into cooler darkness, it can condense before completing the circuit. The missing morning signature is therefore consistent with iron changing state somewhere across the night side. Researchers interpret this as evidence that metallic vapor may form dense droplets and descend through darker cloud layers. The phrase iron rain describes that physical possibility. It is not a direct photograph of weather. Stand for a moment at the edge between the two hemispheres. Behind you, the day side glows under continuous radiation. Ahead, the light weakens into a permanent night where the moving gas cools. Invisible metallic vapor crosses the boundary with the wind. As it loses heat, atoms begin joining into heavier particles. What entered the darkness as vapor may continue downward as condensed material, hidden below the region where starlight can reveal it. The two edges of the planet act like chemical checkpoints. At one boundary, astronomers detect what is arriving from extreme heat. At the other, they search for what survived the passage through darkness. The imbalance between them allows chemistry to expose movement that cannot be observed directly. This method also shows why distant weather cannot be understood only through familiar substances. On Earth, clouds are associated mainly with water, ice, and small particles carried by ordinary air. On an ultra-hot giant, the available materials are determined by temperatures high enough to alter metals, minerals, and complex gases. Condensation still follows the same basic physics. The substances involved are simply different. Further observations added another surprise. Barium, an element far heavier than the main gases expected in a giant planet's upper layers, has also been detected high in the atmosphere. Its presence raises questions about vertical mixing and the forces capable of lifting heavy material upward. Gravity should pull dense elements deeper, yet atmospheric motion can keep some of them at altitudes where telescopes detect their fingerprints. Exactly how that transport works remains uncertain. The measurements identify the element, but the full circulation pattern must still be reconstructed through models. WASP 76b therefore offers more than a dramatic phrase about falling metal. It reveals an environment where heat, wind, and chemistry divide one atmosphere into sharply different regions. The day side produces vapor. The evening boundary carries it away. The night side may transform it beyond direct view. By morning, part of the chemical signature is gone. Far above the dark hemisphere, the atmosphere keeps moving, and somewhere below the observable layers, the element may be leaving the sky. Each time BD plus 54868AB crosses its star, the shadow looks different. A solid planet should block almost the same amount of light during every passage. Its size does not change enough from one orbit to the next to create a completely new silhouette. Here, however, the dimming deepens, weakens, stretches, and shifts. The object refuses to repeat itself. That inconsistency became the first clue that astronomers were not observing a clean planetary disk alone. Something much larger and less orderly was traveling with it. The rocky body completes an orbit in about 1 1/4 Earth days. At that distance, the host star pours enough energy onto the surface to heat minerals until some of them escape as vapor. Material rises away from the remaining body and begins spreading along its path. As the vapor moves outward and cools, part of it condenses into microscopic grains. The result is a cloud of mineral dust shaped by gravity, radiation, and orbital motion. One tail trails behind the planet. Another extends ahead of it. Together, they create an asymmetric shadow far wider than the small object producing it. The silhouette is larger than the world. When the leading cloud enters the stellar disk, the brightness begins changing before the rocky body reaches the same position. After the main transit, the trailing material continues blocking light even as the planet moves away. Those uneven edges help researchers determine how the dust is distributed. They also reveal that the escaping grains do not all behave in the same way. Smaller particles respond more strongly to radiation from the star. Larger grains remain closer to the orbital path for longer periods. By comparing the changing shape of many transits, astronomers can estimate the approximate size and arrangement of the particles. Models suggest grains ranging from roughly 1 to 10 micrometers across. That is comparable to the scale of fine smoke, airborne dust, and some grains of pollen. Yet the cloud stretches across a region many times larger than the body it came from. Imagine starlight passing through that extended veil. The central planet may produce only a compact dark mark. Around it, a broad stream of particles softens the edges and changes the amount of light removed. Each crossing leaves a different fingerprint because the cloud is constantly being created, dispersed, and rebuilt. The transit does not merely show where the object is, it shows what the object is losing. The escaping material may contain minerals once buried in the crust, the mantle, or deeper layers. That possibility makes the dust scientifically valuable. Rocky interiors normally remain hidden beneath surfaces that telescopes cannot resolve from such a distance. Here, the star is stripping material away and spreading it into a form that can interact with light. Future observations may reveal chemical signatures carried by those grains. They could provide clues about the composition of a small rocky world without requiring astronomers to see its surface directly. The process is gradual rather than explosive. The planet is not expected to vanish during a sudden flash. Orbit after orbit, a small amount of material escapes, cools, and joins the surrounding stream. Researchers use the changing transits and dust models to estimate how quickly the mass is being removed. Those calculations are consistent with a small body, possibly one with a mass similar to the Moon. The estimate is not a direct measurement of the remaining interior. It depends on assumptions about grain size, composition, temperature, and how efficiently the surface releases material. The same caution applies to its remaining lifetime. Models indicate that the object may survive for only several million more years. On a human scale, that sounds almost permanent. Within the lifetime of a planetary system, it is a brief, final phase. Catching such an event is statistically rare because the period of visible destruction is much shorter than the billions of years many worlds remain intact. The bright host star makes this particular case unusually useful. More light passes through and around the dust, giving instruments a stronger signal to examine. That signal changes because the cloud never settles into a permanent shape. One orbit may release more material than another. A shift in surface activity may thicken one tail while radiation thins another. The rocky source keeps moving through its short year, while the debris spreads in front of it and behind it. Nothing about the loss needs to be dramatic in a single moment. Its power comes from repetition. A thin layer disappears. Another cloud forms. The next transit arrives with a slightly altered outline. Given enough time, the body that created the stream will no longer possess the same mass, surface, or identity. It is still a planet, yet part of it already exists as a trail of mineral particles. Every orbit leaves it slightly less complete than before. TOI 849b looks roughly the size of Neptune, yet it carries close to 40 times Earth's mass. That combination creates an immediate problem. A planet with those dimensions would normally contain a deep envelope of hydrogen and helium surrounding a much smaller interior. This body is far too dense for that familiar structure. Its size suggests a giant, but its weight points towards something much more tightly packed. The mismatch resembles two sealed containers with the same outer dimensions, except one holds light gas, while the other contains compressed metal and rock. Astronomers measure the radius when the object crosses its star and blocks part of the light. They estimate the mass by tracking the small motion its gravity produces in the star. Together, those measurements reveal a density that ordinary Neptune-like models struggle to explain. The dense world circles its sun-like star in less than one Earth day. At such close range, temperatures rise to roughly 1,500 degrees Celsius. The region where it sits is sometimes called the hot Neptune desert. It is not an empty area in space, but an observed shortage of Neptune-sized planets on extremely tight orbits. Smaller rocky bodies are found there, and larger gas giants can survive, while planets between those categories appear less often. That shortage suggests that many intermediate worlds lose their envelopes, move elsewhere, or never form in large numbers under these conditions. TOI 849b may be one of the rare survivors. One leading explanation is that it began as a much larger gas giant. Intense radiation could have heated its upper atmosphere until gas escaped into space. This process, called photoevaporation, removes material when stellar energy gives atmospheric particles enough speed to break free. A major collision offers another route. An impact involving another massive body could have torn away much of the outer gas while leaving the interior behind. In either case, the present object would be the exposed remnant of something once far larger. Picture Jupiter with its visible clouds removed layer by layer. First, the bright bands disappear. Then the deeper hydrogen is stripped away, followed by the enormous pressure that normally hides the central structure. What remains would not necessarily be a bare metal sphere. It could still contain dense gases, superheated fluids, rock, and heavy elements arranged under crushing pressure. The comparison only shows what astronomers are trying to infer. They are not looking directly into an opened planet. They are using the missing envelope as evidence. The atmosphere that is no longer there may tell the most important part of the story. There is also a different possibility. The world may never have acquired a large hydrogen and helium covering in the first place. Planet formation begins while gas and dust surround a young star, but the available material and timing vary. A solid core can grow quickly enough to pull in gas, yet that opportunity does not remain open forever. If the surrounding disk disperses too soon, a massive interior may be left without the expected envelope. Under that scenario, the object is not the remains of a stripped giant. It is a planet whose formation stopped before the usual final layer arrived. The present measurements cannot yet choose decisively between these histories. Each explanation begins from the same evidence: a Neptune-sized radius, an unusually high mass, a short orbit, and very little gas compared with an ordinary giant. Future observations may detect traces of the remaining atmosphere and place stronger limits on its composition. Those signals could help distinguish between gradual loss, a major impact, and incomplete gas collection during formation. Until then, the interior remains hidden behind inference. Planets like Jupiter and Saturn conceal their deepest structures beneath thousands of miles of gas. A body with much of that covering removed may offer a rare indirect view of what giant planets build around. It also weakens the idea that present appearance tells a complete history. A small-looking world may be the residue of a giant. A dense body may represent either destruction or interrupted growth. Here, absence is not an empty space in the data. It is the central clue. The missing atmosphere is the record that remains. GJ 367b completes an entire orbit in roughly 7.75 hours. A full year there lasts less than a normal working day on Earth. The object moves so close to its red dwarf star that morning, afternoon, and evening have no useful meaning. One side remains turned toward the light, while the other faces away. Before astronomers could ask what its surface might look like, they first had to determine how large and heavy it was. The transit revealed the radius. Each time the body crossed its star, it removed a small and repeatable amount of light. That dimming showed that the sub-Earth is only about 3/4 as wide as our planet. Mass required a different measurement. As the object moved around its orbit, its gravity pulled the host star slightly toward and away from Earth. Researchers detected that movement through tiny shifts in the star's spectrum. The method is called radial velocity. Combined with the radius, it showed a mass close to half that of Earth. Those two values allowed astronomers to calculate the bulk density. The result pointed toward a body with an unusually large proportion of heavy material. Early studies produced a striking interpretation. They suggested that much of the interior might be dominated by iron, making the object an extreme relative of Mercury. That conclusion spread easily because it offered a simple image. A small planet had been reduced almost to metal. The measurements, however, never revealed a solid iron sphere directly. Density can narrow the possibilities, but several internal arrangements can produce similar results. An iron-rich center, rocky layers, temperature effects, and tidal distortion all influence the final estimate. A newer analysis has therefore produced a more moderate picture. That preliminary work favors an iron fraction broadly comparable to Mercury's, or perhaps somewhat greater, rather than an interior made almost entirely of metal. The revision remains a preprint and has not yet become the final word. It still shows why composition claims must be handled carefully. Astronomers are reconstructing the inside of an object they cannot open, touch, or resolve as a surface. They know its width. They know how strongly it pulls. From there, physics provides a range of possible interiors rather than a single photograph. Recent observations with the James Webb Space Telescope added another layer to the picture. Webb measured infrared light as different parts of the planet rotated through view. The day side appeared extremely hot and dark. Very little warmth seemed to reach the hemisphere turned away from the star. That contrast matters because a substantial atmosphere would normally carry energy around the globe. Winds would move heated gas away from the illuminated side and soften the temperature difference. Here, the redistribution appears weak. The evidence is consistent with little or no substantial air surrounding the body. Picture the permanent day side beneath the red dwarf. The surface absorbs stellar energy without a thick layer of gas to spread it elsewhere. Large regions may remain molten under the continuous heating. Across the boundary, the light falls away. The night side receives almost none of the warmth that a deeper atmosphere could have transported around the planet. One hemisphere glows, the other remains far colder. The exact surface composition is still poorly constrained. Darkness in infrared. Measurements does not identify every mineral present or reveal the precise depth of any molten region. It shows how the body handles heat. That response supports the picture of a nearly airless, tightly bound rocky object. GJ 367b also demonstrates how quickly scientific descriptions can change. A first estimate may suggest an almost pure iron interior. Better measurements and improved models can replace that dramatic claim with a more cautious range. The world remains unusual without needing to be simplified into a metal ball. Its short orbit, compact size, high density, and sharp temperature contrast already make it scientifically valuable. Every conclusion comes from small changes in distant light. Those changes reveal the outline, the pull, and the flow of heat. The interior itself remains beyond view, reconstructed one measurement at a time. WASP 107b is almost as wide as Jupiter, yet it contains less than 1/10 of Jupiter's mass. That contrast makes the world look like a giant whose outer layers have been spread across far too much space. Gravity should have pulled those gases inward as the world aged and cooled. Instead, its outer gases remain remarkably extended. A large radius combined with a small mass means that much of the body consists of light material arranged in a broad envelope. The gases occupy a huge volume, rather than pressing tightly around the interior. Early models struggled to explain why the world had not contracted more. As internal heat escaped, the outer layers should have settled closer to the core. The observed radius refused to match that expectation. Recent measurements from the James Webb Space Telescope and Hubble offered a more complete explanation. The data point toward a larger interior core than researchers once assumed. A smaller hydrogen and helium envelope surrounds it, while heat generated inside the world helps keep that envelope expanded. The object is therefore not merely a loose ball of gas. Its structure includes a substantial hidden center and an expanded envelope held open partly by energy from within. One source of that energy may be tidal heating. The orbit is slightly non-circular, so the star's pull changes as the planet moves. That changing force repeatedly flexes the interior. Deep material is compressed and released in a continuing cycle. The process converts orbital motion into heat, much as repeated bending warms a material even when no flame touches it. That energy slows the contraction that would otherwise shrink the gaseous envelope. It resembles an overinflated structure supported from inside by warmth that never fully disappears. The comparison is imperfect, because the giant has no rigid wall and no single surface. Pressure changes gradually through layers of gas, fluid, and denser material. Still, the underlying idea is clear. Heat can delay collapse. That same expansion makes the object easier to study. When WASP 107b passes in front of its star, some starlight travels through the outer gases before reaching Earth. Different molecules remove different wavelengths from that light. The missing patterns reveal chemical fingerprints across a region much larger than the deeper interior. Picture a thin band of starlight passing through gases spread over an enormous distance. Some wavelengths disappear into sulfur dioxide. Others interact with silicate clouds and additional atmospheric material. High above, helium escapes into space in a faint stream. The upper layers become visible not because astronomers can photograph them, but because they alter the light behind them. Hubble revealed helium leaving the highest layers. the detection showed that the expanded gases are not perfectly contained. A weak gravitational hold at high altitude allows some particles to escape. The same property that makes the world appear so large also makes its outermost material easier to lose. Webb and Hubble later provided a richer view of its chemistry. Sulfur dioxide showed that stellar light drives active chemical reactions in the upper layers. Silicate clouds were also identified, although their exact form, altitude, and movement remain model-dependent. The observations do not provide weather footage of grains racing through the sky. They reveal absorption patterns interpreted through laboratory data and atmospheric models. Vertical mixing offers one explanation for how material from deeper regions reaches detectable heights. Rising gases can carry compounds upward before they settle, react, or condense. Stellar radiation then changes the chemistry further. The result is a dynamic envelope shaped by internal heat, incoming light, escape, and circulation. The newer picture also changes how the core is understood. A larger concentration of heavy material means the body did not need an impossibly massive gas envelope to reach its present radius. Internal heating can keep a more modest envelope spread outward. That combination brings the measured mass, size, and spectrum into better agreement. It remains a model rather than a direct view into the interior. No telescope has looked beneath the clouds and photographed the core. Researchers infer the hidden structure by finding a model that reproduces several observations at once. The mass must fit. The radius must fit. The atmospheric chemistry and escaping helium must also fit the same physical picture. WASP 107b remains oversized, but it's no longer unexplained in the same way. Its broad gaseous covering records energy rising from within, while stellar light reshapes the chemistry above. The expansion that created the mystery now provides the long path through which distant starlight reveals the answer. A small point of light sits inside a broad ring of gas and dust around the young star PDS 70. It does not mark a finished planet moving through a clean and settled system. It marks a body still gathering material, while the larger structure around it continues to change. PDS 70 lies roughly 370 light-years away. The system is only several million years old, young enough that much of the raw material from its formation still surrounds the star. That material forms a protoplanetary disk, a rotating sheet of gas and dust from which planets can assemble. Within the disk, astronomers found a wide gap shaped by growing planets, whose gravity redirects nearby material. At least 2 protoplanets move inside that opening. PDS 70b became the first forming planet clearly imaged within such a disk. The image is not a close photograph with visible clouds or a solid surface. It is processed observational data that separates a faint planetary signal from the glare of the star and surrounding dust. Even so, the point of light matters. It shows a planet during a phase that usually remains hidden. The broad disk circles the star. Inside it, the gap contains the growing planets. Around PDS 70b, smaller scale material appears to form another rotating structure. At the center of that local system, gas continues to fall toward the planet. The arrangement is nested at several scales, like rotating currents contained within larger currents. The star anchors the widest motion. The protoplanetary disk turns around it. The planet moves through the gap, while its own surrounding material follows a tighter path. Every layer exchanges momentum, heat, and matter with another. Hubble observations added direct evidence that PDS 70b is still growing, The telescope detected ultraviolet radiation from extremely hot gas falling toward the planet. Ultraviolet light carries more energy than visible light and can reveal matter heated to high temperatures during accretion. Accretion is the process by which a forming body gains mass from its surroundings. As gas moves inward, gravity accelerates it. The material can become hot enough to glow at wavelengths that reveal the ongoing transfer. From that signal, researchers estimated the present growth rate. The measurement does not mean every incoming stream has been mapped. It shows that material is reaching the planet now. The detailed route remains uncertain. Gas may move from the broad stellar disk into the gap, gather around the protoplanet, and circulate through a smaller disk before falling farther inward. Magnetic fields may also help guide some of the material, although the exact process is still under study. The observations confirm accretion. The complete pathway remains a model. The material surrounding the planet may eventually serve another purpose. A circumplanetary disk can become the place where moons form. In our solar system, the regular orbits of large moons around giant planets suggest that smaller disks once surrounded those planets during their growth. PDS 70b offers a possible view of that structure before it vanishes. Gas and dust circle the planet, collide, settle, and perhaps begin building smaller bodies. The process is not guaranteed to create moons that survive. It reveals the environment in which such formation can begin. This is what makes the system different from the mature solar system around us. Here, most of the original gas has dispersed. The planets follow established paths, and the raw material is largely gone. Around PDS 70, the architecture is still being negotiated. Gravity opens gaps, material crosses boundaries, planets gain mass while also reshaping the disk that feeds them. The growing body changes its environment, and the changing environment controls how much more it can grow. That exchange cannot continue forever. As the disk thins, the supply of gas will weaken. Radiation from the star will help disperse what remains. The protoplanets will settle into a more mature arrangement, and the evidence of active formation will become harder to see. For now, the system preserves a short phase that usually disappears before astronomers can observe it. The light reaching Earth began its passage hundreds of years ago. During that time, PDS 70b continued gathering matter and moving toward a form we have not yet seen. We observe the planet as it was. It continues becoming something else. The debris disk around HD 106906 forms a broad visible region around a young pair of stars. Most of the known structure appears organized within that flattened ring. Then the scale expands outward. Far beyond the disk, separated by hundreds of times the distance between Earth and the Sun, a massive companion continues to orbit the stellar pair. HD 106906b carries roughly 11 times Jupiter's mass. Its orbit is not only distant, it is also strongly elongated and tilted away from the plane followed by the debris. That misalignment makes the body difficult to explain through a simple formation story. Planets usually begin inside disks of gas and dust, where particles collide, gather, and slowly build larger objects. The farther a body lies from the central stars, the thinner and slower that process becomes. At the present distance of this giant, conventional accumulation would struggle to create so much mass before the original material dispersed. The orbit therefore raises a question that the current position alone cannot answer. Did the object form where it is now, or was it pushed there later? One modeled explanation begins much closer to the binary stars. The young giant may have formed inside the denser part of the system, where material was easier to collect. Gravitational interactions with the central pair could then have changed its path. A close encounter would not need to destroy the body. It could transfer enough energy to throw it outward onto a nearly escaping orbit. The process is known as gravitational scattering. Instead of moving through a smooth circular path, the giant would have been redirected by a short and powerful exchange of motion. The result could resemble a stone flung from a rotating sling, except gravity, rather than a cord, controls every part of the movement. Once pushed outward, the object may have approached the point of leaving the system entirely. A passing star has been proposed as a possible final influence. Its gravity could have altered the outward path just enough to keep the body weakly bound instead of allowing it to escape. This sequence remains hypothetical. No observation recorded the original encounter. Astronomers test the possibility by combining the present orbit, the shape of the debris disk, the motion of the binary stars, in computer simulations. The model shows that such a history could occur. It does not prove that it did. Other formation routes remain possible. The giant may have formed through a faster collapse of gas, more like the process that creates a small star than the gradual buildup expected for ordinary planets. That possibility matters because the object's mass lies near a debated boundary. Bodies heavier than most planets but lighter than stars are often called brown dwarfs. They never become massive enough to sustain the long-term hydrogen fusion that powers a true star. Yet mass alone does not always provide a clean classification. Formation history may be equally important. An object assembled inside a planetary disk may be treated differently from one created through the direct collapse of a gas cloud, even when both end with similar masses. HD 106906b sits close to that uncertain division. Its identity depends partly on a past that cannot be watched directly. Imagine moving outward from the central pair. The debris disk first fills the view as a wide band of scattered material. Beyond its edge, the density falls sharply. The host stars shrink into a brilliant double point. At the position of the distant giant, most of the system would seem compressed into a small region far behind it. The surrounding space would be sparse. No nearby ring would make the object's membership obvious. Only gravity would show that the connection had not been broken. The orbit is like an extremely long thread stretched between the companion and the stars. The thread is weak compared with the tight bonds inside the debris disk, but it continues to hold. One circuit may take many thousands of Earth years. Across that span, the body moves through regions that feel almost interstellar. Its remoteness also makes the orbit difficult to measure. Hubble observations taken over many years record only a small fraction of the complete path. From those changes, researchers estimate the direction, tilt, and elongation of the orbit. Each new measurement narrows the possibilities, but the full motion remains far longer than a human lifetime. The planet, therefore, challenges more than one definition. It sits beyond the visible architecture of its own system. Its mass approaches the uncertain border between giant planets and brown dwarfs. Its possible history includes both planet-like growth and star-like collapse, and its current orbit may preserve the result of an ancient gravitational disturbance that almost removed it entirely. The companion remains attached to the binary pair. The connection is faint, stretched across an extraordinary distance and visible only through the slow curve of its motion. Gravitationally, it still belongs. From almost every other perspective, it seems to exist at the edge of leaving. The word planet usually suggests a complete object. It brings to mind a stable sphere, a settled orbit, and a structure that has already become what it will remain. Exoplanet astronomy has made that definition harder to preserve. Some worlds are still gathering mass, others are losing gas, shedding rock, or carrying the remains of an earlier form. A body may begin inside a disk, grow into a giant, lose most of its outer layers, and continue circling as something that no longer resembles its original state. None of those moments has to be the permanent version. Planet may describe a phase. Formation does not stop at one clean boundary. After a world gathers enough material to become recognizable, migration can move it toward a different region of its system. Radiation can erode an atmosphere. Collisions can remove layers or rearrange the interior. Tidal forces can generate heat long after the original disk has vanished. Gravitational encounters can stretch an orbit until the object almost leaves its stars behind. Every present measurement, therefore, contains part of a history. Mass reveals what may remain inside. Radius shows how widely that material is distributed. Orbital motion records the influence of gravity. Timing can uncover bodies that no telescope sees directly. Spectroscopy identifies chemicals through the wavelengths missing from light. Direct imaging can locate a young object while it is still embedded in the material that feeds it. No single method gives the complete picture. Each one opens a different window onto a process already underway. That limitation matters because the confirmed population now exceeds 6,000 exoplanets. The catalog sounds enormous, yet it is shaped by what instruments can detect most easily. Large bodies create stronger signals than small ones. Short orbits produce repeated transits in less time. Extreme heat can enlarge atmospheres and make chemical signatures easier to measure. Favorable viewing angles allow planets to cross their stars from Earth's perspective. Quiet worlds on distant paths may remain hidden simply because their signals are weaker and slower. The most unusual discoveries are therefore not proof that most planets are extreme. They are the cases that current methods are especially good at finding. Detection is not a neutral window. It has a shape. Imagine a distant system containing several calm, small worlds and one inflated giant close to its star. The giant may dominate the observations because it blocks more light and completes many orbits, while the smaller bodies barely reveal themselves. The resulting catalog records reality, but it does not sample every part of reality equally. That is why every new discovery changes both knowledge and expectation. A strange world can reveal a process that may also operate more quietly elsewhere. An escaping atmosphere shows how radiation alters planets over time. A forming giant reveals what mature systems no longer display. A body near the border between planet and brown dwarf forces classification to depend on more than mass alone. Formation history becomes part of identity. The boundary is drawn in pencil rather than carved in stone. It shifts as observations expose objects that occupy the space between familiar categories. A giant can become a core. A rocky body can become a stream of dust. A forming object can remain unfinished for millions of years while still being called a planet. The language must stretch because nature does not arrange itself according to the names created for it. those names remain useful. They allow astronomers to compare systems, organize measurements, and ask better questions. They become dangerous only when the category is mistaken for a permanent physical truth. The map of planetary possibilities is still unfinished. Many regions remain nearly blank because the worlds there are too small, too cold, too distant, or too slow to reveal themselves clearly. New instruments will fill parts of that map, but they will probably blur other borders at the same time. Each added object may answer one question while making the definition less comfortable. Light also places a final limit on what is known. Every distant planet is observed in the past. The farther away it lies, the older the arriving information becomes. While its light crosses space, the body continues to cool, orbit, lose material, gain material, or respond to forces no observer can yet measure. The object seen from Earth is not the object as it exists now. It is an earlier version. Somewhere in darkness, a distant world has already changed. The evidence of what it became is still traveling toward us.